Java and...
No. Good. I think you can get, I think you can view samples of this on Amazon. And yeah, it teaches discrete structures.
Why can't that be your test?
I was thinking about it, because it's actually really well written from what I saw. Yeah, I'm never there when it gets presented, so that's okay.
I'm guessing it's odd house too.
That would be good.
So for 250, we're recommending this. What did he do?
I don't know where I put it, but anyway, I was curious afterwards, and I found the original document from MIT talking about the fact that they were using NOR gates and why they made that decision. And it was based on weight versus reliability were the two dominant factors that led them to this decision. And then it talks all about the design of the gate and stuff like that. It's a cool document. All right. Does anybody here want an unclaimed homework? All right. Eventually someone will say, hey, if you're on camera and you want the unclaimed homework, let me know. Meet me in the middle of the bridge at midnight.
Get today's newspaper.
Bring the appropriate bribe.
Bring unmarked quarters.
I was thinking more like chocolate chip cookies or.
Oh yeah, that would work. All right, so let me twist this over. That's going to be pretty horrible.
I feel like move it back and probably.
I don't really feel like I need to capture this, but we'll make the viewers pukey anyway. Yeah. Alright, so I promised you some Minecraft.
Yes. Oh, yeah.
So let's do 250 world. There we go. So I cobbled this together for 250 classes, but since we're talking about Gates and De Morgans, we can use it here, or at least some of it. So, cut off on my sign. Okay. So we start off over here, and this is a NOT gate. So first of all, how many people here have played Minecraft or know of Minecraft?
Know of, how to play.
Know of, okay. It's basically, it's just a really cool game. You dig stuff up from the ground and you build things. And there's a survival mode and a creative mode. I'm in creative mode, so I have access to all kinds of things in my inventory. And there's an element called redstone. And if you mine redstone, you can use it to make basically things like transistors. They don't work exactly like transistors, but they have the same general idea. It lets you, among other things, build logic gates. And you can find wikis on this. So what I've got here is an inverter, and it's by putting this torch on this side of this block and putting some redstone going into it. And redstone by itself acts like a wire. And if it's bright, that's carrying a logic 1. If it's dark, it's carrying a logic 0. So you can actually experiment with digital circuits inside Minecraft. And you can build things like traps so that when a zombie comes close to your house, it'll open a trap door and stuff like that. People have actually built like complete working computers inside Minecraft.
I've seen those.
And this was stuff that the creator said he never imagined.
There's a mod somewhere where somebody actually, I think it's called Industrial Craft.
Yeah.
And somebody built this mod for Minecraft so you can have a computer with really rudimentary scripting.
Mm-hmm. Cool. Yeah, I also saw a 3D printer someone did.
There's
Like gather blocks up and
in-games good thing.
place them according to a program.
The craziest thing I saw was
Gmod and
somebody had made Minecraft inside of Minecraft.
Oh, nice.
Like they actually built like fully with the red set and everything
Very
inside
good.
of Minecraft. It's just
That's
cool.
excellent. All right, so here's a basic inverter, and I have a piston over here. It's just a thing that can raise up or lower depending on whether it gets a 1 or a 0. It's getting a 0 right now, so it's in the lower position. And my switch, when it's in this position to the left, that's a 1. And if I click on it, it will flip over to the right, that's a 0. My redstone goes off, and my output goes to a 1. So this block in here is acting like an inverter, and my output's high while the input's low. And if I flip this, then the input's high, the output's low. So that's basic inverter behavior. Wait,
I'll have to play with Minecraft at some point.
okay, yeah, there's a wiki that tells you how to make all these gates. So moving over to hole number 2, here's an AND gate. And my switches, they're in the 0 position right now. And this is the output over here. So if I flip this switch, nothing happens. And if I flip this switch, nothing happens. But if I flip them both, then my output goes high, and it starts to snow. So we'll clear up the weather.
Was it supposed to snow or was it just random?
It's just random. Same with chickens who like walk across in the middle of this.
It's time set.
Thank you. So there's an AND gate, right? And if both of these switches are on, then the output is high. If either or both of them is low, then the output is off. Okay, keep that in mind. And let's look at our next gate, which is a NOR gate. So again, I've got two switches. These are in the 0 position and the output is high already. So an OR gate goes high if either input is 1. A NOR gate goes low if either input is 1. So if I flip this switch to the 1 position, my output goes low. And if I flip this to the low position, my output goes low, or to the on position. And if I flip them both, the output stays low. And it's only when they're both low that the output is high. So that's a NOR gate, right? But close your eyes for half a second and open them and look at this differently. Suppose I think of these switches as being a 1 over here and a 0 over here. Isn't this just an AND gate? And if they're both over in this 1 position, the output goes high. And if either or both are 0, the output's low.
So it's just like an inverted AND, right?
Yeah, so what is it? Is it doing an AND or is it doing a NOR? De Morgan's theorem. It's doing the same thing. It's the same circuit. It's looking at it 2 different ways. Right? And this is this idea of duals that pop up in Boolean algebra and engineering and physics and so on. It's really just 2 sides of the same coin. So De Morgan's theorem, it can be a kind of horrifying mathematical exercise, or it can just be this simple. It's really just 2 sides of the same thing. There's an AND gate, or maybe it's a NOR gate. All right, so what's going on over here? This we haven't talked about, and I don't think I'm going to spend time talking about this in here. But in 270, we talked about sequential circuits as opposed to combinational, 250.
Yeah.
Combinational circuits have inputs and an output. You can write a truth table. Sequential circuits, their behavior depends on their history. And looking at the inputs is not sufficient to tell you what the outputs of the circuit will be. So they have memories. And the starting point for a memory can be as simple as this. This actually has no inputs. but its output is unknowable at any given time, unless you know what its output was a moment ago. And if I know that this output was a 0 a moment ago, then I know that this will be a 1 and a 0, and this is going to change to a 1.
Do these actually exist with like some kind of clock?
You can do this for a cheap clock if you're not too worried about accuracy. If you just want a way to oscillate, you can use 3 inverters. Theoretically, you can do this, but it doesn't actually work. The propagation delays are too small. But you can go next door, you can take a 7404, hook 3 of them together, put an oscilloscope on the output, you can actually see it. It's really sloppy. It's not a nice clean square wave, but it definitely oscillates.
You like the 555?
Yeah. And it's a whole lot easier to hook up than a 555.
It doesn't get pissed off when you put a little thing there when you're monitoring
Yeah.
the house.
Or you forget to connect ground because it's not electrons. All right, so these other things are just flip-flops and memories built from this idea of cross-coupled NOR gates, which is really just a stretched out version of that's just a stretched out version of that. And when we pulled up those schematics yesterday, I'm horrible at finding stuff. There we go. When we pulled that up, somebody pointed out that there's these cross-coupled NOR gates like this. Those are flip-flops, they're memory elements. And in 250, of course, we study those, we build state machines from them and so on and so forth, and I don't really want to go into that in 215. But we do that, we beat it to death in 250. But in 215, not next week, but the week after, so week 9, we are going to talk about state machines. And we're going to talk about them from a different perspective. From the perspective of things like syntax checking or language parsing or things like that. And from the perspective of computing in the abstract sense of computing. And we'll talk about Turing machines and other things like that. So I don't want to talk about sequential machines here, so let's stick to combinational elements, and let's talk about arithmetic. Which I might have spelled wrong. Have we actually talked about binary numbers yet in this class?
No, it's pretty much been assumed.
But we know binary numbers, right? Because we've been tossing them around. So it's a weighted positional notation. Okay, this means 2 to the 0 plus 2 to the 1 plus 2 to the 3. That's 1 plus 2 plus 8. That's the decimal number 11. So we can represent decimals in binary. We can convert binary to decimal and so on. So if we have some decimal numbers, that's a decimal number 5, here's a decimal number 7, and we want to add them, we can add the same way that we normally add numbers base 10. We can go column by column. 1 plus 1 is 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 0 is 1, and that's equal to 12, which is 5 plus 7. So pencil and paper addition works with binary numbers, and it's actually easier than adding decimal numbers. Because to add decimal numbers, you need to know what 6 plus 2 is, you need to know what 8 plus 3 is, you need to know what 9 plus 7 plus that 1 that you carry is. You just got to know those things, there's no way to get them. So before we do this, we learn these addition tables, at least up through 9 plus 9, and we memorize them and we get tested on them and all this pain and suffering. And then we use those to do this kind of addition. With binary numbers, what we have to remember is really, really simple. So we need to remember 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1, or each of these when we have a carry. And if we know how to add in each of those 8 cases, we're done, as opposed to 100 cases with decimal. And there's actually fewer cases than that. So we talk about a 1-bit adder. It takes in 3 bits, A, B, and an incoming carry, and produces a sum and a carry. And you can write a truth table. And this covers all 8 of those cases. And these, right, our incoming carry is 0. And you can fill out exactly what these should be in each case. You end up with something like that. And this is typically called a full adder. And the nice thing about a full adder is, well, a full adder only adds 1-bit numbers. You can put 2 of them together and make a 2-bit adder. And this is one of the labs we do in 250. And if I change the way that my system diagram looks, here's A and B, here's my carry in, here's my sum, and here's my carry out. So if that's my full adder, and I want to make a 4-bit adder, it's really easy to do. There's a 4-bit adder. You put in 2 4-bit numbers, A0 through A3, B0 through B3, you get out a 4-bit sum, and you get out a final carryout, which you can treat as your 5th sum bit. And if I want a 1,000,000-bit adder, I can just repeat this 1,000,000 times, and there's a circuit that'll add 2,000,000-bit numbers. Really easy to lay out. And just to close the loop on the 250 part of this, each of these has an incoming carry, and the incoming carry is just fed by the outgoing carry of the previous stage. But this least significant bit, there is no incoming carry. Right? When you add numbers, that first column, you always have an incoming carry of 0. So this actually just gets hardwired to a 0. And if you're actually building this, there's no point in building something that adds 3 numbers if your third number is always 0. So we actually change this to a circuit that only takes in 2 bits, generates a sum and a carry. And that's what we call a half adder. It's just a hobbled version of a full adder. But that's just an embellishment if you're actually like putting parts on a proto board. In general, we can just make all of these full adders and just feed a 0 in the rightmost one. So if we do this n times to add n-bit numbers, the circuit looks exactly the same. What's the problem with this? This is not what we actually do in practice. Why not?
Because then we need a separate subtractor.
We can actually turn this into a subtractor with...
Well, that's, I don't know what you were leading to.
Are we saying a practical reason? Or
Yeah, there's a practical reason more than
It's
Do you want
very,
space?
subtractor.
it's very slow
It's very slow. Why?
because it has to carry each output from each adder and it has
Yes.
to wait for the previous. So the fourth one would go after every other one has gone.
Right. So we don't know what this sum bit is until we know what this carry in is. We know these bits immediately because they're being supplied by, something that's got the 2 numbers we're adding. But we don't know if this is a 1 or a 0 until the stage before it has done its addition. And it doesn't know what this bit is or what its carry out is until it knows what its carry in is. And this goes all the way back. And in the worst case, you have something like this. And until I add these, I don't know this carry is a 1, and until I add those, I don't know this carry is a 1, and so on. And that carry has to ripple all the way down the chain. So if you have 1,000,000 of these full adders, it takes you 1,000,000 propagation delays. Where the propagation delay is the time it takes this thing to add 2 bits in incoming carry and generate this outgoing carry. And it's usually like 3 levels of logic or so. So long propagation delays. We don't usually add 1,000,000 bits inside our hardware, but we typically add 32 or 64. So is this a problem? And it's a factor. It causes some concern, but by itself it's not a huge deal breaker. But it still does cost you speed. So there's a lot of work that was done, I think mostly in the 60s, to speed this up. And I want to talk about 2 approaches to this. And this is stuff that if I had extra time in 250 I would talk about it, but I almost never do. But it's cool stuff. So we'll talk about it here. The first is a CLA. That's a carry look-ahead adder. And the idea is, can we generate the carries coming out of an adder without rippling them? Is there some way to look ahead and know what the carry bit is going to be coming out of an adder before you've actually generated all those other carries and rippled them through? And the answer is yes, and it's based on the following notion. Here's a full adder. There are exactly 2 cases where this is going to have an outcoming carry. So carry out equals 1 if and only if. And there's 2 possibilities. The first is that the addition that you do in here the A and B generates a carry. So your incoming carry is 0, but both of these are 1. That's going to generate a carry. So you generate a carry, meaning A and B are both 1. So they give you a value bigger than 1 bit. Or you propagate a carry. In other words, there is an incoming carry, and based on the values of A and B, that ripples on into the next stage. That's called propagation of the carry. And we can write equations for these two conditions really, really easily. So we're going to generate a carry from stage I if both AI and BI are 1. And we're going to propagate a carry if either AI or BI are 1. Right? If at least one of these is a 1, then and only then, if we have an incoming carry, we'll get an outgoing carry. If both of these are 0, but A and B are both 1, doesn't matter if we have an incoming carry or not, we're going to generate an outgoing carry. And so our carry coming out, so carry out of stage I is the following equation. Either we generate a carry from stage I, or we propagate a carry from stage I and we have a carry from stage I minus 1. So we'll get a carry out of the 5th stage if the 5th stage generates a carry or it propagates a carry, and we got a carry out of the 4th stage.
So this is kind of recursive then.
Yes.
Only kind of.
Now that you mention it. And like all good recursion, we can unroll it. We can stretch it out and turn it into something non-recursive. So our carry out of stage 0 is either we generate from stage 0 or we propagate from stage 0 through stage 0 and we had a carry coming in from stage minus 1, which doesn't exist. There is no carry going into stage 0. So our carry out of 1 is out of stage 0 is just generate 0.
So this is kind of like the base case then, because
It's the base case.
Like C in is always 0.
C in is always 0. So that's where we begin.
Okay.
All right, and now we can plug in and we can go forward and find what CI is for any I we choose. So C1 will be either generate 1 or propagate 1, carry 0. C2 will be generate 2 or propagate 2, carry 1. C3 will be generate 3 or propagate 3, carry 2. And now we're just going to go crazy and plug things in. So I shouldn't have erased these. There's where our generate propagates are. So this is G1 or P1 G0. This is G2 or P2 ANDed with C1, which is G1 or P1 G0, equals G2 or P2 G1 or P2 P1 G0. And C3 is G3 or P3 ANDed with all of this stuff. Which is equal to G3, or P3, G2, or P3, P2, G1, or P3, P2, P1, G0. And this is just a sum of products. And if we have 4 input AND gates, it takes us 2 propagation delays total to calculate each of these AND terms and then to sum them together. And the PIs and GIs are just these simple combinations of our inputs. So what we can do is we can create a 4-bit carry look-ahead adder and another 4-bit carry look-ahead adder. And I should have a carry in from term n minus 1 here to do this. I got greedy. And this inside here can be a ripple carry adder. So it'll take it a handful of propagation delays to come up with its correct sum. But in parallel, this CLA is also doing its 4-bit addition, and the next CLA is doing its 4-bit addition. And I have a total of 8 of these things, and each of these 4-bit carry look-ahead adders is computing its sum at the same time as every other one. So in the 4 propagation delays that it takes to do my, well, back up from that. This will calculate its ripple carry sum, and it takes a bunch of delays. It takes 4 ripples, and each ripple takes 3 or 4 propagation delays, depending on the circuitry inside. But in basically 2 propagation delays, this will generate the correct value for its carry out. And as soon as it does that, this can start doing its addition. And 2 propagation delays later, it will know its carry out, and this next stage can start doing its addition.
So you may not have the addition done, but you've at least got the carries.
But you've got the carries done, yeah.
Can go. Okay.
And once you have that carry, you can do the rest of the addition, and its ripple carry takes a little while. But these other stages upstream aren't waiting for you to finish your ripple carry addition. You've already generated the carry. So that speeds things up pretty significantly. But it's still a ripple effect. We've just broken it, in this case, from rippling 32 times to rippling only 8 times. And if you have the hardware budget, you can extend this. You can make a 64-bit carry look-ahead adder. But your terms over here are going to be an AND of 64 inputs, and that's expensive hardware to make. So we usually only do this for small blocks, 4 bits, maybe 8 bits. But it's faster than a ripple carry. So that's one speed up, but that's not the really cool one. Let's talk about the really, really cool one. And this is still used inside computer chips today. And the idea here is a carry save adder. If you think about when we're adding numbers and we write the carry down over this next column, and we add those and we write the next column with a carry on top, we're rippling that carry over, but it's really because we're adding these things one column at a time. We're the reason that we have to do this ripple. And there's a way to get around that. And this is called a carry save adder. So here's the idea. Let's compute this sum. Let's add these 5 numbers together. Let me tell you why we want to do this first. Well, we multiply numbers. So we want to multiply these binary numbers. Again, we can use what we do with pencil and paper with decimal numbers. But our task is a lot easier. If this digit is a 1, we multiply this number by 1. If it's a 0, we multiply by 0. Both of those multiplications are trivial. Multiplying by 1 just gives us 1, 0, 1, 1, 0, 1, 0, 1. Multiplying by 1 gives us 1, 0, 1, 1, 0, 1, 0, 1. Multiplying by 0 gives us nothing. We don't have to add that, but I'll put it down just to line things up. Multiplying by 1 gives us 1, 0, 1, 1, 0, 1, 0, 1, and so on. And when we're done, we need to add all of these together. And that's the slow part of multiplication, adding all your partial products. 64-bit numbers, you have 64 partial products to add together. And if each one is a ripple carry and takes 180, 192 propagation delays, that's a really expensive piece of hardware to use, because you have to do that 64 times. So a carry save adder is designed for being able to add a set of numbers together efficiently. And here's how it works. Let's add the numbers 5, 6, 7, 8, and 9. So there's 5, there's 6, there's 7, there's 8, and there's 9. And you and I have more fingers than computers do, so we might say 1 plus 1 is 3, and we could carry that over with an extra carry and so on. But for a computer, it would basically say add those together, rippling the carries, and then take that and add the number 7. So 1 and 1 is 0 with a carry, that's a 1 with a carry, that's a 1 with a carry, that's a 0 with a carry, and so on. Okay, here's the idea of doing carry save. So take our first 3 numbers. There's a 5, there's a 6, there's a 7. And let's add those together, but we're not going to ripple the carries. So first we're just going to add them and just write down the sum. 1 plus 1 is 0, 0 plus 1 plus 1 is 0, 1 plus 1 plus 1 is 1, 0 plus 0 plus 0 is 0. That's the sum. And now I'm going to write down the carries, moved over 1 spot. So 1 plus 0 plus 1 generates a carry of 1. 0 plus 1 plus 1 generates a carry of 1. 1 plus 1 plus 1 generates a carry of 1. Zeros generate a carry of 0, and zeros generate a carry of 0. And there's a 0 here also. If I add those two things together, I will get 5 plus 6 plus 7. Because each of these is the number that I would have written over here when I continued doing my addition. Right? That's what we do with carries. We add them to the next column over. So instead of adding them when I wrote down the sum, I just wrote down the sum, but I wrote another number consisting of just the carries, moved over 1 column. And if I add this and this, I'll get 5 plus 6 plus 7. Right, so this is 4, and this is 14. That's 18, that's 5 plus 6 is 11, plus 7 is 18. And I can generate this number at the same time I'm generating this number. Totally independent operations. Because I'm not carrying anything over. I'm not rippling. So one set of propagation delays gives me the sum and the carry. And now, so this was 5, 6, 7. Now I'm going to add my number 8 to this. And I'm going to add these 3 numbers the same way. I'm going to get a new sum. Zeros give me a 0. That's a 1. That's a 0, 0, 0. And my carries, that's going to be a 0, 0, 1, 1 will give me a carry. 1, 1 will give me a carry. Now I've got 24 plus 2 is 26. Did do something wrong. So that's a 0, that's a 0, that's a 1, that's a 1, that's a 0, 0, 1, 0, 0. I made a mistake somewhere.
How come you do that?
I think it was in your first calculation of your carry.
No. This carry or this carry?
That one right there.
This one.
Yeah, I think, but I might be
That's
wrong.
a 1, that's a 1, that's a 1, that's a 0. I think that's okay.
That's okay? Okay.
Yeah.
Are you saying 18 plus 8 is 22?
Yes, this is right. So 5 plus 6 is 11, plus 7 is 18, plus 8 is 26. And this is 24 plus 2 is 26. So we're still right. So 5, 6, 7, 8, let's add our last number, 9. And I'll continue this over here. So my sum bits will be 1, 1, 0, 0, 1. And my carry bits will be 0, 0, 0, 1, 0. 0, 0, 0, 1. And now I have to add these together using a ripple carry adder or a carry look-ahead adder or something traditional. So 1, 1, 0, 0, 0, 1. 32 plus 3, this looks like 35. Is that the right answer?
Mm-hmm.
It is. Awesome. And how many things did I have to do? I had to do one pair of calculations, a second pair of calculations, and I just had to do a final addition. And in general, to add n numbers takes me n minus 3 operations.
So you just lose 3 flat.
You just lose 3 flat plus some sort of ripple carry addition. But adding these is a lot faster than doing a ripple carry addition, right? Because this is just, it's just A XOR B XOR C, and the carry is just AB or BC or AC. Right, we can calculate each of these bits in parallel, because the value we're going to put down here does not depend on any of these other bits. So we do roughly order n operations to add n numbers, and we don't have to do the expensive ripple carry until we get to our very last operation. And that's a whole heck of a lot faster than ripple carrying here, and then adding this and ripple carrying, and then adding this and ripple carrying, and then adding this 9 and ripple carrying.
Is it n minus 3 or n minus 2?
Something like that. It might be n minus 2.
Because we do for the first operation too.
Yeah. But the important part is it's on the order of n, but those n adds we do take a fixed number of propagation delays, regardless of how big our word is. Whereas if we do ripple carry, the number of propagation delays varies with the number of bits. And so it's basically n squared propagation delays versus n. And it's quirky, but it's because it's different from how we do things pencil and paper, but it's really the same thing we're doing. We're just deferring dealing with these carries until later. And in fact, we keep deferring them until we get down to this final stage. And only then do we actually like add the carries. So that's a carry save. But we can do even better. So if we want to do this carry save, this takes us roughly n operations to add n numbers. But remember, all this stuff can happen in parallel. So here's a 9-bit Wallace tree. So we want to add 9 numbers together. And I'm just going to show you the circuitry for adding 9 bits using a carry save chain. And we'll array this out 32, 64 times whatever. So here's our numbers, A, B, C. Put those into a carry save adder. D, E, F. Put those into a carry save adder. G, H, I. Put those into a carry save adder. And each of these produces a sum and a carry. So we'll take these and we'll add those with a carry save adder. And we'll take these and add them with a carry save adder. And we get a sum and a carry from each of these. And there's a carry save adder. And it gives us a sum and a carry save add. And now we've got 3 numbers, and we add those, and then we put this into a ripple carry or a carry look ahead. And it takes us 1, 2, 3, 4 propagation delays, because this all happens at the same time, these happen at the same time. And if you do this for, say, 64 bits or some larger number, the total propagation delay comes out more like log of n. Because we bifurcate in a tree. When we talk about trees next week, we'll see log n a lot. So we go from n squared down to n down to log n if we put this in a Wallace tree. And that's what goes on inside a lot of CPUs. They have Wallace tree multipliers.
I was just writing this. I was going to ask, why don't we do this?
Yeah, we do. All right, so that's a little bit about arithmetic and how some of this digital logic unfolds in practice. And we still use some of these techniques. Surprisingly, when you get to things like 500 or 1,000-bit multiplication, this stops working. Because at the scales that we're using in hardware, the propagation delays along the wires becomes the dominant time factor. And we start losing the advantage of this. So other things need to happen. So like encryption hardware and Bitcoin hardware and stuff like that, we're facing new multiplication challenges. But this works for most normal cases. All right. We will start talking about trees and graphs on Monday.